Hello and welcome to today's session, Real-Time Bidding Caching Use Case on the Google Cloud Platform. My name is Matt Bichelle, Senior Director of Product and Solutions Marketing here at Aerospike. I'm pleased to be joined by Archit Pandey, who's Technical Fellow, Senior Director of Engineering at VDXtv, and Manoj, Principal Engineer at VDX. A little bit about this session. VDX does global advertising real-time bidding, but largely through video platforms. The fact that they are hosting their service on Google Cloud Platform is fantastic. A lot of our customers at Aerospike use cloud, and we love to hear use cases on GCP. Despite Aerospike working so well in VDX that they call it the forgotten system, which is something that Aerospike hears quite a bit. Archit and Manoj still want to take you through kind of their bidding architecture, the fact how they use it for their user profiles, and some of the configuration and management challenges that they have that we think everyone can learn from. So without further ado, I'll hand it over to Archit. Please take it away.
Thanks, Matt. Hello, everyone. It's a pleasure to be here. My name is Archit, and I work as part of the engineering team at VDXtv. I'm also the product owner of the programmatic bidding project. Today, I'm here with Manoj, who works as a principal engineer with the RTV team. We are here today to talk about real-time bidding and caching use case inside it, and how Aerospike fits into all that. So in this slide, I'll get started with a small background of VDX.tv, basically what we do and who we are. But before going into engineering details, we'll very briefly go into how RTB has evolved over time. So VDX.tv is an ad tech company, and we were formerly known as Exponential. We recently rebranded as VDX.tv to reflect what we do. VDX stands for Video Driven Experience. We believe that video is a powerful way to deliver a brand's message to its audience, and the message has to be delivered in a way to influence individual user and the households they live in. So our creatives are built to have a consistent view across different devices. We also connect dots between user devices, households, and show relevant message based on where the user is in the whole customer journey. This creates a bigger impact, and users feel more connected with the brand. I'll leave it here, but if you guys are more interested, you can always check the VDX.tv website. Seeing our live creatives there will hopefully make more sense of all of this. Okay, in this slide, I wanted to go over the evolution of RTV, how ad tech basically started and how we eventually reached here. So this is how the ad tech ecosystem looked probably in mid-90s. It was a very simple setup. There were a bunch of websites. Users on the internet used to visit these sites. And then advertisers who wanted to show ads digitally to these users, they used to connect with these websites. These websites are basically also known as publishers. So once these advertisers put their code or their, the creative of the ad on these websites, users, when they visit the site, they used to see the ad. And advertisers used to pay publishers for these views or impressions. It was a very simple setup, but the problem happened when internet started scaling. There were more websites, there were more users and advertisers. So it grew more and more difficult for advertisers to go to every publisher and get connected with them. Similarly, for publishers, it was a challenge to connect with different advertisers. So a new entity showed up in this, in the ad tech domain. They were known as ad networks. Ad networks had a smarter technology. They placed their code on these websites, but this code was not specific to any advertiser. So what this means is when the request for an ad comes to the network, the ad network could choose which advertiser to show that ad for, and they could optimize the advertiser campaign. This makes it much simpler for advertisers as well as publishers, because they don't have to go and connect with different publishers or advertisers. Ad networks used to take care of all this. The initial companies which started were DoubleClick and Google. VDXtv also started around 2001, so it was pretty early. This setup ran fine for a long time, but then ad tech domain saw a lot of companies coming in. There was more revenue into the ad tech domain. So there were companies which started picking up specific, jobs or to create a niche for themselves. So some of these companies started associating more closely to publishers, and they started calling themselves as SSPs, which are known as supply side platforms. Their job was to optimize revenue for publishers, to connect with different advertisers, and to manage all the work for them. The other set of companies came to be known as DSPs, or the demand side platforms. Their job was to effectively run campaign of advertisers. So ad networks basically kind of vanished and split between SSPs and DSPs. A lot of companies either rebranded as SSPs or DSPs, and some like VDX.tv continued to overlap both on the SSP and DSP side. Again, everything was fine here, but the setup was still very manual. It took a lot of time to integrate. So next, from all this, another requirement came in and a new entity came into the domain. These were known as ad exchanges. So these ad exchanges were very much like ad networks, but the difference was they made it very programmatic. So all the connections and everything was at real time. Advertisers or DSPs don't need to connect to publishers before they show an ad on the site. And similarly, publishers just need to connect to ad exchanges, and ad exchanges used to connect to different DSPs. So the real difference is this changed the whole model of revenue sharing in the ad tech domain. So multiple DSPs can bid for the same request, and they have equal opportunity to get that opportunity to show an ad there. And this made it really programmatic. DSPs and ad exchanges had a connection through server side, and every request they had to bid up certain price to get that inventory. And if the ad exchange gets multiple requests from different DSPs, it used to run an auction to decide who gets to show the ad. So this is where very briefly where we are in the ad tech domain right now. And this is the RTB project that we have. So where VDX.tv fits into this ecosystem. So as I told, we started very early. So we connected both with SSPs as well as DSPs. I mean, we overlapped on both the sides. So we already had a direct integration with websites. So what was the need for us to go to RTB? So the thing was, the ad tech domain and the internet has evolved a lot. And there were new opportunities like connected TV, mobile apps, and there were new publishers coming in every day. So to serve the best interests of our advertisers, we had to get the access of most premium inventory, the biggest scale that we can get, and also new opportunities like connected TV. So this was the premise why we started the RTB project. So when we started connecting with Google AdX, which was the most obvious choice for us. It was the first in the ad exchanges domain. And then they had a reference implementation, how bidders should connect with the exchange. So we started there, and that's how we landed up in Google Cloud as our infrastructure provider, because everything in their reference implementation was very apt for the cloud. So, so this is how we got here. Now, when we connected to the exchanges, currently we are connected to basically 10 exchanges. So when we connected to different exchanges, one of the goal for us was to pick and choose most premium and useful inventory. And making these decisions of which inventory to pick based on just the ad request data was not enough. So what we did was we leveraged most of the solution we had pre-built in the direct integration. For example, our contextualization engine, our algorithms and machine learning models, and our first-party data platform. So like you see in this diagram, we have a bidirectional connection between our RTB system on public cloud to our direct integration system, which resides in our data center. We feel this gives us an edge over other DSPs to us. Okay, the other thing was RTB has a lot of scale because you're virtually connected to every website on the internet, except for the social media, which is like a walled garden. So this creates a huge trade-off for us because we want the premium inventory, but we want an infrastructure to support all that scale. And with the latency requirements, it makes it more challenging because we have to maintain enough resources on our infrastructure to scale and provide the desired latency. So since the initial design and start of the project till whatever we do now, we keep this trade-off in mind. RTB technically is a high throughput and a low latency application, but in my experience, managing cost effectiveness with changing business every quarter makes it much more challenging than a technical project. For example, during initial COVID days last year, the whole world was hit and business was very hardly hit. And to sustain, we had to scale down the infrastructure a lot. Nobody was obviously prepared for it, but I'm glad the way we designed the application, we were able to scale down pretty fast. And when it recovered, we were able to scale it back up. So in the next slide, I'll hand it over to Manoj, and he can go over the challenges, specific technical challenges of the RTB project and how we handle them.
Thanks, Archit. So before we go into system architecture, I want to share traffic and data volume numbers from our RTB platform. It will help us explain engineering challenges, system design, and the choices made much better. Our RTB platform is integrated with 12 different exchanges. During peak hours of the day, more than 250 bidder server process 120 million bid requests per minute. System matches each bid request against the available campaign and respond with P95 latency of 100 milliseconds, including network round trip. We started with the Google Ad Exchange with 100K QPS. We were aware of the fact that we need to reach this scale of 100 million in coming years. The engineering team was cognizant of scaling and infrastructure challenges that will come along, and hence we adopted key engineering goals from day one, like building a platform that auto scales and is cost effective. We outlined various platform automation like infrastructure management, performance optimization, system monitoring, and recovery, and included them in our engineering goal. Let us walk over some of this engineering goal and see how our RTB system design addresses them. The first and most important one is auto scaling, where our platform extensively uses Kubernetes and its horizontal auto scaling capability. Kubernetes autoscaler creates more bidder servers as traffic increases and terminates them at traffic reduce, providing cost-effective and elastic infrastructure. Co-located containers in Kubernetes helped us with efficient resource utilization. To achieve high throughput and low latency, we developed our own JSON boundary data serialization framework and message connect RPC library. We use it in most of microservices communication as well as data storage in our system. We adopted system design technique like caching data wherever possible and followed microservices design pattern like circuit breaker between components. This increases overall throughput and helped us reducing latency. To address platform automation and efficiency, we developed an observability system that tracks key application and system performance metrics. This data is used by alerting, incident management, and health recovery system like bid controller. This helped us regulating volume of bits flowing in and out of the system. This is a high-level architecture of our RTB platform running in US region. A mirror replica of this system is also running in Europe and Asia region. As shown in this diagram, bidders are front-end server which receive requests from Ad Exchange. A bid request represents a user or household and contains context information like encrypted user ID, domain, device, geo, and privacy-related information like GDPR or CCPA. To process a bid request, bidder needs a user profile, household profile, active campaigns, and facing stats. A subset of this data is cached in bidder's local LRU cache. Bidder first look up in its local cache, and if not found, it fetches data from Aerospike database using data API layer. Bidder then evaluates first user profile against advertiser's targeting criteria. After a successful match, it responds to ad exchange with creative detail and bid price. So in this matching process, bidder generates bid decision-making information and various locally aggregated bidding stats, which are ingested into a platform for different optimization and reporting, which I will cover later. Exchanges on another side perform an auction among received bids and then render winning ad in user's browser or device. Creative rendering process and user interaction with ad unit generates impression and data events, which are recorded into bid logs and then propagated to other platform components. Largely, this covers real-time pipeline of our RTB platform and different components involved there. The second part of our architecture is optimization and reporting pipeline. The front-end server of this pipeline accept feedback events, as we saw earlier from ad exchange, impressions and data events from user browser, and ingest them into Kafka cluster. Bid decision-making information and locally aggregated bid stats from bidder server is also ingested into Kafka cluster. Different optimization services and reporting services consume this data and the consumption frequency varies from near real time to hourly and daily. Let us walk over one of optimization service, pacing and price optimization service. This service consumes real-time bidding information, spend and win information for all active campaigns in system. It augments real-time information with the historical information available in Aerospike and then predict pacing rate and spend for future slot. This predicted information is used by bidder servers to pace client spending, and they use for quality inventory, selecting quality inventory, which improves campaign availability goal. So largely this cover real-time pipeline and reporting pipeline. There are some specifics on stream processing, which we can touch later if time permits. Okay, so before moving to Aerospike users and different kinds of data we store in it, let us talk about different stages of bid request processing in bidders. This will help us understand the types of data we store in Aerospike, its access frequency, volume, and significance. So bidder servers process bid requests in 4 stages. The first stage is matching the right advertiser using user profile and household profile. In second stage, all matched advertisers from stage 1 are further filtered using advertiser criteria, brand safety criteria, and privacy restrictions. In stage 3, for each matched advertiser, system computes optimal price using machine learning models and price determination algorithm. In fourth and final stage, internal competition is performed among all selected advertisers, and one of advertiser is selected as a winner, whose creative and price is returned to ad exchange. So as we saw in previous slide, our RTB platform processes more than 100 million requests per minute with 100 millisecond end-to-end network latency. For us, high throughput and low latency are product success metric. And this was evident from very beginning that we need a storage solution that scale horizontally as we get more exchanges integrated with our platform. Aerospike DB matches both of these parameters and came out as a first choice for us. As of date, we are using Aerospike as a primary store and caching layer for all critical information for wherever we need high throughput and low latency. For instance, user and household profile is stored in Aerospike. That is used in first and second stage of bid request processing in bidders. This profile data is updated immediately with impressions as we saw an ad to user. So essentially, this signifies volume and access latency that platform demands from a storage system. The second type of data is bid and spend stats. This data is generated by bidder server at a regular interval but immediately consumed by a pacing and price optimization system. The predicted pacing rate and spend data from this optimization service is stored in Aerospike DB and used for campaign pacing, and inventory selection. So far, we looked at different types of data stored in Aerospike DB. Let us now dive into specific details on how we store this information and some stats around them. So user and household profile data are stored in binary JSON format with user and household ID as a key. They have a TTL of 90 days, but they are removed from the store immediately when required to ensure privacy compliance. There are 2 billion user profiles and 50 million household profiles with an average size of 100 KB. The profile data that we talked about is replicated across Aerospike cluster nodes with replication factor of 3. So far, we looked at Aerospike users in our platform, different kinds of data stored in it, and the predictable latency, low latency access to it. In this slide, we'll dive into specifics of Aerospike cluster. We have Aerospike cluster, separate Aerospike cluster for US, Europe, and Asia region. Each regional Aerospike cluster stores data for that region only. The largest Aerospike cluster we have is in US region with 20 nodes, hosting a 15 terabyte local SSD disk and 300 G RAM, and delivers 350K read QPS. For us, operational challenges related with the storage system was well taken care of by Aerospike, like cluster management is easy and doesn't involve operator overhead. Cluster automatically rebalances data with minimal impact on live traffic. Aerospike cluster and node reprovisionings require minimal effort. We just need to understand characteristics of SSD disk, and then simple math provides resources required for certain data sizes. This helped us, while cluster reprovisioning for tax season. So, though all things looks good, I wanted to share our experience where we spend engineering effort around Aerospike. The first one is daily data cleanup. As we talked in previous slide, we store household user profile for 90 days. We have a daily cleanup job that scans and removes tail data from Aerospike cluster. For us, Aerospike scan job was resource intensive. We tried to lower down the priority of scan job to contain the impact on live traffic, but it did not help much. And finally, we developed a throttling solution on top of Aerospike client. Another challenge that we had was moving complete data from old cluster to new cluster during VPC migration. We tried rack awareness and Saturday solution, but both of them had certain limitations. Saturday was more closer to what we were looking for, but server boot time was considerably high. In the final solution, we landed up using a rolling addition and removal of nodes. This took some time to migrate data, but we did not observe major impact on live traffic. Overall, we started our RTB journey with Aerospike DB and one ad exchange. As business grew, we integrated our platform with 10 more exchanges, and Aerospike DB is scaled with each such integration. I hope this helped you with the technical challenges of RTB platform and how we use Aerospike DB to solve this problem. I will now hand over presentation to Archit.
Thanks, Manoj. So I'll very briefly go over the roadmap that we have for this year and the coming next year. So as you know, cookieless internet is one of the things which is bothering the ad tech domain. And next year, Google is going to make changes. So this impacts us as well. And we are relying on Aerospike to handle all the data. We expect there will be an explosion of ID and user profiles. And we plan to keep all that data in Aerospike. So we have not seen any challenges with Aerospike before. As I was telling Matt before, it has been running so smoothly and so stable that we even forget at times that we are running a database at the back end. So this is going to fit into Aerospike, and we look forward that Aerospike is able to handle it. Then we also plan to do hybrid cloud this year and remaining of this year and the next year. And we are looking at solutions from Aerospike for cross data center replication to handle that. Then obviously there is always more data into the system, and there is latency improvement that we have to do. And and for all that we have Aerospike, we are relying highly on Aerospike for all this. So finally, this is the team that we have today in our project. We are a small 6-people team. Yeah, that's it. I'll hand it over to Matt.
Thank you again, Archit and Manoj. A great thorough walkthrough of real-time bidding on GCP. If you have a couple moments, I'd like to take us through some questions. The first question, I think, Archit, you had touched on the value of Aerospike not just being the performance, but also helping manage costs. And you alluded to the ability to scale down as well as up. Could you give a sense for the magnitude of the amount, maybe in a percentage of how great that was, and also how quickly you were able to scale?
Yeah, I mean, we almost scaled down our costs to about probably around 65% of the total infrastructure cost. And this includes a lot of CPU, which came out of, obviously, Aerospike was part of it. A lot of scalable infrastructure we had to reduce. We also made some changes, which we had planned to make since a long time, but we were not able to prioritize them. But because of the scenario of COVID, we had to take it up on priority, and we did that. So there were some optimizations on usage of CPU as well. We did that.
Yeah, that's certainly a significant portion. I know other customers are on GCP, and they also do scale. They initially launched, or at least portion of their platform on GCP with similar percentages.
Mm-hmm.
Actually, Manoj, you talked, I saw a lot of the reference of machine learning models within your architecture. I wanted to know, given the nature of your machine learning models, how frequently are you updating them? And yeah, and what can you describe what that process is with Aerospike?
I can answer the question now if you want.
Either, yeah.
Sure, go ahead.
Right now we are building models every day, once a day. We are deploying them once a day, but we keep training these models every few hours. We don't deploy it very frequently because, I mean, it has to learn and then act on it. So we don't want it to be too volatile for our campaigns. So a lot of data we keep is, be it the user profile or any kind of browsing profile that we keep. All that data along with third-party data, it's there in Aerospike. So when we build the models, it's a lot of processing that we do, to generate that data for the model training. So, and Aerospike is our only source right now. So we have a pre-processor which was there in the diagram that Manoj had shared. So it takes up, it takes all the events data from, real-time Kafka pipeline, then merges it with the Aerospike data, and then dumps that data into a certain format which the machine learning models can use. So there's a lot of sampling that we do because too much of data isn't, machine learning doesn't need a lot of data to process. It works very well on a sample of data.
So you're really targeting what you're using is what I'm hearing.
Mm-hmm.
Something else that you guys had mentioned was the need to maintain compliance with GDPR and CCPA. Could you give a little bit of color on how Aerospike is helping or facilitating the management of data for that?
Yeah, I mean, there are different kind of regulations, and we follow all of them as per their requirements. Sometimes we have to scrub data based on requests from a user. And those are the things which are more, CPU exhaustive because we have to go and look for all the data for those particular requests, and then we have to scrub them out of Aerospike. There are some other kind of regulations which require us not to target behaviors on particular user's browser. So the structure that we maintain in Aerospike, we have provisions of privacy embedded into it. So we can, based on different regulations that we follow, we basically mark those profiles as per it. So for example, somebody does, wants some regulation based on GDPR, and they don't want it to be behavior targeted. So we basically enable that flag for that user IP or any profile. And then these are excluded from all the targeting campaigns. And similarly, for scrubbing, we have to go and we scan Aerospike. And as per whatever the timeline for that privacy regulation is, we have to scrub all that. So we have written processes which help us do all this. But since most of our data is there in Aerospike, we do have to run scans on it. But thankfully, the scrubbing part is not very frequent, but it is CPU intensive. So it takes a while for us to scrub it.
Well, at least it can be executed at a very, very granular level, I imagine. For the new capabilities of bin level shipping across data centers, that could also help.
Yeah, thankfully, because of the fast lookups that we have in Aerospike, we can basically scrub them as per the timeline requirements that the regulation has. Okay. So we've been doing okay with it.
Perfect. I almost have to apologize. We're already over time. I want to extend a big thank you again to both of you, particularly to Manoj. For those who don't realize, he is calling from India. So it is nearing 2:30 in the morning. So it has not gone unnoticed. Aerospike does thank you. And hopefully you each will be open to people reaching out to you, because there was a lot of content that was covered, covering Kubernetes and microservices, as well as your experience in GCP. So it was excellent. So again, we thank you, and thanks everyone. Have a good rest of your summit.
Thank you so much.
Thanks, man.